This is problem number 29 from chapter 8. It is about two piloted satellites approaching one another, and these satellites are colliding elastically. So let's first take a look at the information we have been given. We've been told that the relative speed is 0.250 meters per second. We've also been given the mass of object number 1 and the mass of object number 2. Finally, we were told that they are colliding elastically, and we are asked to find their final relative velocity. So how are we going to use this information to somehow solve this problem? Because we haven't been given a lot to begin with. The most important piece of information we've been given is that these satellites are colliding elastically, which means we know two things. Number one, momentum is conserved. So the momentum at the beginning equals the momentum at the end. And number two, the kinetic energy is also conserved. So kinetic energy at the beginning is the same as kinetic energy at the end. Finally, we also know that the relative speed of these satellites is 0.250 meters per second. Relative speed means in relation to one another. So we have, if the satellites are approaching each other, we would have one satellite moving, we can say to the right in the positive x direction, and another moving maybe to the left in the negative x direction. So this can be satellite 1, and this could be satellite 2. All we know is that relative to one another, the speed is 0.250 meters per second. So that would mean the velocity, for example, of satellite 1 plus the velocity of satellite 2 is going to be equal to 0.250 meters per second. Since we can see that the second satellite is moving in the opposite direction to the first satellite, we could also write this as V1 minus V2 equals 0.250 meters per second. They would both be true, since this would be a negative value. Now, how are we going to use that to figure out their final relative velocities? Let's start by writing out the conservation of momentum. Okay, so we have PI, and that's going to be of the first satellite initially, so I'll say satellite 1 initially, plus the momentum of satellite 2 initially is going to equal the momentum of satellite 1 at the end, and it will, that plus the momentum of satellite 2 at the end. We can even go ahead and replace momentum with mv. So the mass of the first satellite times the initial velocity of the first satellite, and then I'm going to replace all the other information. Mass of the second satellite times the velocity of the second satellite initially. That equals, again, mass satellite 1 times the velocity of the first satellite at the end. And we're going to do the same thing for the second satellite, and that's going to be the second velocity at the end. Great. Now, both of these objects are moving, so we can't cross out any of our terms. Nothing is just automatically going to go to 0. What I could do, however, to simplify this a bit, is to gather my M1 terms and my M2 terms on the same side. So I'm actually going to, I'll move this over here by subtracting, and I'm going to move this term to the other side. So we'll subtract that. And that's going to leave me with M1 V1 initial minus M1 V1 final equals M2 V2 final minus M2 V2 initial. And from there, I can simplify just a bit further by pulling out the m terms. So I would have mass 1, and then just the initial velocity of the first satellite minus the final velocity of the first satellite is equal to m2 times the final velocity of the second satellite minus the initial velocity of the second satellite. I do have masses, but plugging those in right now isn't really going to be helpful since we don't actually know any of the terms, the actual values for any of the other terms in this equation. So that's as far as we are going to be able to get with the momentum equation. Now let's go ahead and use the kinetic energy equation. And remember, kinetic energy is 1/2 mass times velocity squared. I'll go ahead and do this part in green. Okay, so this was all for momentum. Now the same will be true for the kinetic energy. The kinetic energy of the first satellite initially plus that of the second satellite initially will equal the kinetic energy of the final satellite initially. Of the first satellite at the end plus the kinetic energy of the second satellite at the end. We can replace our terms, so we have 1/2 mass 1, velocity 1 initially, and that's squared, plus 1/2 mass 2, velocity 2 initially, and that's squared. We'll do the same on the other side, so mass 1 and squared plus 1/2 mass 2, velocity 2 final squared. Because we have this half present in each part of our equation, we know that the half is going to cancel out, so all my half terms will cancel out. And I'm going to do the same thing that I did for the momentum equation. I'm going to gather the m1 terms on my left side, and I will gather the m2 terms on the right side. So I'll be moving this term over here, and I'll be moving that term to the right. So then I would have m1 v1 initial squared minus m1 v1 final squared equals m2 v2 final squared minus m2 v2 initial squared. And finally, we can simplify just a bit more. I'm going to go back to using green. So we have m1, and then that would be v1 initial squared minus v1 final squared equals m2 v2 final squared minus v2 initial squared. So now we have two equations that we have simplified seemingly as much as possible. And upon first glance, it might not be obvious what we could do to make them look more similar. So I can't really do anything with this momentum equation up here. I have simplified that as far as I possibly can. But we could apply an algebra rule to this equation in order to get rid of our squared terms. So remember, if we have a squared, or whatever you want to say, a squared, x squared, b squared, c squared, it doesn't matter. So a squared minus b squared, that is going to be the same thing as a plus b times a minus b. So applying that here, I would actually end up with, and I will do this part in another color, I'll use purple. So I'm going to rewrite this, separate it a little bit. So now we're going to have m1, so then this would actually turn into v1 initial plus v1 final times v1 initial minus v1 final. Okay, so we've just simplified the left side a little bit more. We're going to do the same on the right. m2, and this would be v2f plus V2 initial, and then times V2F minus V2 initial. So now I have simplified the kinetic energy portion as far as I possibly can. And I'm going to just highlight the two equations I have. So here's what I've gotten so far, this and this. And if you look very carefully, I hope you notice that there's one part of each equation that actually looks the exact same. So I have this term here. Well, I guess technically we could do this either way, but I'm going to choose this side. So M1 times V1 initial minus V1F. Well, if I look, I have that. I have M1 being multiplied by V1 initial minus V1 final. So knowing that, I could actually just substitute what M1 V1 initial minus V1 final is equal to. And because I know that this term here is actually equal to M2 multiplied by V2F minus V2 initial, I could just substitute that and continue working the problem. So let's go ahead and do that. So now this is going to become V1 initial plus V1 final, and then I'm going to substitute this part. So I have M1 multiplied by, here I'll do it like this, brackets, V1 initial minus V1 final, and that equals, and then the other side I am going to leave that alone. Oh, I apologize. Hold on. What did I just do? This should say what it is equal to, not the same part, that was my fault. Okay, here it is. So this would actually be M2, I apologize for that, V2F minus V2 initial. And that is equal to, so now I'm going to write what's on the other side of my equation, M2, and then V2F plus V2I, and V2F minus V2I. So if I'm once again looking at both sides of my equation, I see that I can cross out a couple of things. Number one, I have an M2 term on both sides. And number two, I have this V2F minus V2I term on both sides. So that will also cancel out. Then the only part of this equation I will now be left with is V1I plus V1F equals V2F plus V2I. And that shows us that for object number one, the initial and final velocities added together will be the same as the initial and final velocities added together for object 2, or for these satellites. So I can even rearrange this so that I end up with a term that looks like what I had in my original relative velocity equation, so that it looks like this. So I'm looking for V1 minus V2, and remember, this was initially, because initially that was the relative speed, the relative velocity. So then I want my equation to say V1 initial minus V2 initial. So all I have to do is move this term to the left side, and I'll move this term over to the right side. So that would give me V1 initial minus V2 initial equals V2 final minus V1 final. Okay, well now I can replace this with what we know it equals, and that's 0.250. So 0.250 meters per second is equal to V2 final minus V1 final, meaning that the relative velocity after these two satellites collide is equal to the relative velocity before they collided. And we just went through the math to prove that. So if you ever need to work a problem where you have two objects colliding elastically, and both of those objects are in motion initially and at the end. You can always just use either, I will highlight these in yellow, you could use this formula, or you could use this formula, how we've rearranged it, it really doesn't matter. And you could solve for whichever piece of the equation you are missing. I hope this helps.